Hi, everybody. Thanks for joining us. I'm going to wait a few moments as the attendees come in. Okay, it looks like we've stabilized a bit. I want to thank you all for joining us for the second session. I hope you enjoyed the first session. This session features several talks that are listed here. And they're covering a range of topics, as you can see, and I'm quite excited to hear our speakers today. So without further ado, I think I would like to ask Jeremy to start sharing his slides when he is ready. And while he does,
it's saying you need to stop sharing. Sorry.
Oh yeah, try that again. Yep. Thank you. Okay, our first speaker today is Jeremy Hare, who's joining us from NASA Goddard Space Flight Center. Is going to talk to us about crowdsourcing X-ray source catalogs with an eye towards machine learning. Remember to put your questions into the Slack if you can, and if you can't, you can put them here in the Q&A. Thank you. Take it away, Jeremy.
Thanks for having me. So yeah, today I'm talking about crowdsourcing X-ray catalogs with an eye towards machine learning. And this is work I've done with these collaborators, and I'd like to note that most of the coding that's gone into this project has been done by Igor Volkov. So X-ray catalogs in general are an essential part of astronomy. Some of the earliest catalogs include Ptolemy's, which was published in like 150 AD. But then the Book of Fixed Stars, which was published in about 964, included actually Andromeda in the LMC and was included objects outside of the Milky Way. And cataloging continued until today, but some of the most popular catalogs are the Messier catalog, which, as you probably know, many of the sources like M87 get their names from this catalog. And the New General Catalog, which was published in 1888, also still many sources and objects contain the NGC title in their name. This tradition's continued until today. There are many catalogs like the McGill Online Magnetar Catalog, the ATNF Pulsar Catalog, Intermediate Polar Catalogs, Black Cat, which was a black hole low mass X-ray binary catalog, spanning a large number of different objects and multi-wavelength features. And there's good reason for this. Catalogs eventually help our understanding. And some examples of this are, for instance, the gamma ray bursts, which as more and more were cataloged and their durations mapped, we were able to understand that there are actually two populations of long and short duration bursts, which actually have different physical underlying mechanisms driving the emission. Another more recent example is the environments of fast radio bursts, where cataloging repeating fast radio bursts have allowed us to follow them up with higher angular resolution radio telescopes and to locate their host galaxies and map out their environments. And also populations of exoplanets, TESS and Kepler have helped us uncover many more exoplanets and help study the relationship between their mass and radius and their host star populations. But there's still a large number of limitations for catalogs. For instance, they're often single source catalogs with no kind of unified format for their multi-wavelength properties. Some of them can even just be single band. For instance, the ATNF Pulsar catalog doesn't include X-ray only or gamma ray only detected pulsars. And they're often useful for comparison, but not classification. And what I mean by that is that if you have a source and you know it's a pulsar, you can plug it into the pulsar catalog and compare properties like E dot, surface magnetic field, things like that. But if you have a source and you don't know what it is, it can be hard to aggregate all the data from these catalogs and make comparisons to try to figure out what your source could be. And this is becoming increasingly more important as we continue to grow the number of X-ray sources detected with catalogs like the Chandra source catalog version 2, which has over 300,000 sources. Most of them are serendipitously detected, so don't have a classification. We also have, XMM also has a catalog, which has about 500,000 sources. And as we keep moving in more and more into the time domain era, eROSITA has already finished its first all-sky scan and has over 1 million X-ray sources. So being able to aggregate catalogs and compare multi-wavelength parameters is becoming increasingly important if we want to understand these sources and try to find more interesting sources. However, there's several issues pertaining to catalogs. For instance, they're often very time-consuming to construct, and even more so to upkeep. You have to constantly be looking through the literature to update the catalogs to make sure they don't go out of date. Very frequently, they're not funded, or it's difficult to get funding. And oftentimes, because of these two former features, they become outdated relatively quickly. And it's kind of a testament to that. While I was searching for catalogs in the first, on one of the beginning slides, I ran into this quite frequently, where the catalog is just no longer existent in any sort of online database. So one way to overcome a lot of these issues is to crowdsource these catalogs. So one of the kind of first catalogs to do this was the Open Supernova catalog, which is shown here. And the nice thing about this catalog is it allows people to add their own supernova. You can see with this button here, and even provide things like light curves and spectra for individual supernovae. And the authors of this website even made the catalog very general so that other people could use this architecture to create new catalogs. And you see some examples of those here. However, the problem is that there's still single source type catalogs with no real communication between the different source types. So a lot of the work I'm going to describe here was kind of heavily influenced by this. I really like this idea, but it still didn't have all the features that we wanted. So we developed this catalog called X-Class. And basically it started as a training data set for a machine learning pipeline. I'm not going to talk about that pipeline in this talk, but there are more talks later this week, one on the 19th by Hui Yang, who will go more into detail about the pipeline if you're interested, and some results from our pipeline on the 19th and the 26th. So this catalog contains 9 source types, which are commonly detected in X-rays, like active galactic nuclei, neutron star binaries, which are the redback and black widow type millisecond pulsars, cataclysmic variables, low and high mass X-ray binaries, low and high mass stars, and young stellar objects. And these are pulled from literature verified sources, which right now just kind of common catalogs like ATNF and the HMXB catalog by Liu et al. And currently we're pulling all sources from the Chandra source catalog version 2. There's no real reason we have to keep it limited to X-ray only catalogs, but that's what we were interested in, what we started with, but we could grow this pretty easily. And we also have an XMM version coming soon. So basically, we've taken all of these source classes and cross-matched them also with the Gaia 2 mass and WISE all-sky surveys to include all their multi-wavelength information. So the catalog is currently available here. I can drop this link in the chat after the talk. We've also got a research note published here, and this is just an overview of the catalog. I have a video here showing how it works. So at the top here, you see we have a number of different source classes that you can turn on and off. And then we have a number of different features here. So for instance, the X-ray flux versus some different hardness ratios, variability metric, Gaia G-band magnitude, X-ray to optical flux ratios, and you can also choose various colors from the different surveys. And then again, you can turn on and off the classes just by toggling the buttons at the top. We also have a feature selection or object selection feature. So say you make this plot and you're interested in what HMXV this is, it's an outlier. You can click it and you'll see the name pop up, a number of the different parameters, such as RA-dec and G-band or J-band magnitude if it has it. And then the current reference catalog we're pulling things from at the moment to create these source classes. So those were features that have existed on this website since basically we published it. But now we've added some new features, which we've just very recently, I think last night, pushed to the website. And these include this lasso feature, which if you click this button here, you can encircle any number of sources you want here. And if you scroll to the bottom of the page, you'll find this table button. And when you click it, basically the selection will show up of all the different sources that you selected with whatever features are already highlighted in the table. And then you can turn on and off these different features that will show them in the table. And we have these CSV, Excel, and PDF buttons, which unfortunately currently aren't working due to a bug. But once we get that fixed, you'll be able to click that and basically download whatever table you create. So if you want to do other plots or search in Simbat or something like that, you can do that. It's accessible that way. We've also added a Aladdin dropdown to all the sources. So if you click a source, you'll basically get a zoom in of your source in Aladdin, which has all the capabilities of Aladdin, which I'm sure people are familiar with. But you can also click this layered button and plot a whole bunch of different types of surveys. So right now this is 2MASS, but you could also do pan-stars, DSS, SDSS, I think Eximum Newton's in here as well. And we've also just added the feature to upload your own sources. So the easiest way to do it at the moment is basically if you go to this help option, you can click this example and it will download a kind of template file, which has sources in it, but of course you can just replace those sources with your own sources. You can choose that file and load it in, and it will basically make these plots with all the sources you just loaded in. If you give the sources classes, they will show up in the class colors that are represented here basically by the different classes we have. And then you can go through all the different multi-wavelength plots to see how basically your sources compare to those of the known population, or if your source is unidentified, what kinds of source classes it most closely resembles. So there's still a few features in progress that we're working on that are not live yet. But basically the website structure is sufficiently generic to be reusable. And we're now working on creating source class specific web pages. So as an example of this, here's a class specific catalog. So basically this is cataclysmic variable subclasses. Currently we just have one. There are many like polars, intermediate polars, etc. This is just the intermediate polars. But the purpose of having these class specific catalogs is to include more features that are individualized to each class. So for instance, AGN don't typically have orbital periods. So it would be difficult to do these kind of on a broad scale, but these are more similar to the kind of class catalogs you're used to. So here we're plotting the spin versus orbital period for a number of intermediate polar cataclysmic variables.
2 minutes.
Okay, thanks. So basically these living, an example workflow of how we want these kind of living catalogs to work. So this is from a paper we recently published where we were looking at unidentified integral sources. One of these sources from a previous paper was confirmed to be a CV, but wasn't sure whether it was a polar or intermediate polar. So in our recent work, we found a spin period in the X-ray data and then confirmed an orbital period through radial velocity curves. So basically what you would do then is you could take this source and upload it to this intermediate polar catalog and plot the spin versus orbital period and see what other kind of intermediate polars look similar to your source. So here you can click on this source and you find the name of the source, and then you can either do a literature search or go see what similar characteristics your source shares with other sources. And then actually the living part of these catalogs. So the idea would be then, we found this intermediate polar cataclysmic variable. This feature is currently disabled, but there will be an upload button. Basically you upload, you choose the file, which will be your CSV, which will include all the multi-wavelength information, your email address, and link to the paper. And then basically it will be reviewed by us and added to the catalog, assuming things are correct. So in this way, basically, we can create a living catalog that can stay up to date as astronomers discover new sources and upload them via this interface. And in the kind of distant future, we're also planning on having source-specific pages. For instance, here, this is a redback pulsar, a millisecond pulsar. We have Simbad, the actual Chandra image from the Chandra source catalog version 2. And then we'd also love to incorporate kind of modern optical time domain data. So for instance, from here from ZTF and tests where the light curves are available, you can see the periodicity in the light curve here folded. And this is just the raw unfolded light curve in tests. You can just see the periodicity by eye. And then we would have these class tables, which would include additional information that wouldn't be shared across multiple different classes. And one point I'd like to make is that making these data products like light curves easily accessible helps make these pages much easier to produce. So for finding the, for instance, there was some difficulty finding the X-ray light curves in an easily accessible way. So towards machine learning, basically these living catalogs are kept in a machine readable and kind of standardized format across all classes. They can easily be downloaded and used as a training data set for machine learning. This takes the burden away from a single person or group to maintain these catalogs and allows for many groups to build custom training data sets suitable for their science case. So let's say you're looking at an X-ray source population in external galaxies. You might want to remove low mass stars, for instance, as you're not going to expect to detect those. In addition to that, you can also have different flags, which can be used for different environments, for instance, globular clusters or again, nearby galaxies. So yeah, while I was making this talk, I couldn't help but think of this XKCD comic, which I've edited a little bit. But thank you for listening, and we'd appreciate your feedback on XClass if you do have some time to use it and play with it. Thanks.
Thank you for that, Jeremy. Very interesting talk. I apologize I gave you the warning too early. I had to join from my phone because of my connectivity issue. So if there was anything you wanted to expand on, do feel free to do that.
I'll just jump back really quickly and just say in these class tables, just some different things you could think about having in the for these objects. Things like the subclasses, distance measurements, whether you get them through Gaia, for instance, if they have parallax distances or other means. Spin and orbital periods, companion masses, for instance, in this case, a neutron star mass, the companion type. And then you can also track the references very easily in this way. And this would help, for instance, if you need to do a literature search for some source, it would all be contained in these web pages and you could easily access those. I think that was the only thing I went through very quickly.
Great. Apologize again. We have a question from Rafael Martinez Galarza, who asks, tells you thanks for a great talk. This is really exciting for the Chandra source catalog and other catalogs. And the question posed is, how did you deal with X-ray matching the Chandra source catalog with Gaia? What matching algorithm did you use given the differences in error ellipses? And how did you deal with ambiguous matches?
Yeah, so it's a good question. And it's kind of a long answer, but basically we used AstroQuery once we got the Chandra sources matched with the catalogs. So for the smaller classes, I'm just gonna go here. So these numbers in parentheses are the numbers of sources in each class. So for the smaller classes, we actually went through by hand, more or less, and did a literature search to see if the companion was kind of confirmed in the literature or not. And if it was, we kept it. If not, we made a note of it and threw it out. Obviously, this is a lot of work and it's gonna be very difficult to do for a huge fraction of sources. Like the XMM catalog is much larger. And we were unable to do that for AGN and things. But I hope this would be where the community could help a lot, where, you know, we've done things, if you notice something's off or something's wrong, you can send us a message basically saying, you know, this counterpart is incorrect, and we can go back and reiterate and work our way through this. But yeah, it's a lot to do for a single person to verify every single cross match.
Thank you. Other questions for our speaker? I'll ask a question. I think some of us are familiar with Zooniverse. Do you intend to have any kind of that level of interaction?
Yeah, I honestly haven't really thought about that much. It's a little hard for me to think of how you would make it like accessible to the general public, because it's kind of specialized in a lot of ways in terms of like confirming things. So I think it would be difficult, but if anybody has any good ideas of how it could be done, I am certainly all ears.
Right. Thank you so much for your talk, Jeremy.
Thanks for having me.
Will our next speaker please share their slide? Hi, Shifu Zhu. Our next speaker is Shifu Zhu from Penn State University. He's going to talk to us about investigating the nature of nuclear X-ray emission from radio loud quasars. Take it away. Shifu.
Hi, can you hear me?
I can hear you, yes.
Okay, hi. Today, I will talk about the nature of the nuclear X-ray emission from typical radio loud quasars. Since the 1980s, standard picture has been that the nuclear X-ray emission from most radio loud quasars largely arise from their jets. However, based on a correlation, model fitting, and model selection analysis of a large high-quality sample, we find that the nuclear X-ray emission in most of the radio loud quasars is still largely arise from the corona. And we select our quasars from the Sloan Digital Skies Array quasar catalog, and we constrain their radioluminosity and radio band spectral slope using the first NVSS and VLAS surveys. And we measure their X-ray fluxes using Chandra and X-Newton archival observations. And so most of our X-ray data is serendipitous. And we clean our sample using their multivalence colors and optical UV spectrum to remove these objects with red colors and broad observation lines. Our final sample have a size of more than 700, and almost all of them have a radio band slope measured. Therefore, we could divide the sample into flat spectrum radio quasars and steep spectrum radio quasars. We find that the LX-LUV correlation for the steep spectrum radio quasars is always consistent with that for radio quiet quasars, shown in this black line. It's only that the normalization of this correlation is larger in steep spectrum radio quiet radio quasars. And furthermore, if we divide the sample into beams of radio loudness parameter log R here, their consistency in slope is persistent. It's only that the normalization factor increases with the log R. So it suggests that in this steep spectrum radio quasars, the corona dominates X-ray emission, and furthermore, there is a corona jet connection at work. To confirm this, we perform the model fitting and the model selection. The models we consider here, one is for the so-called jet scenario. The X-ray can be divided into two components, one from the jet, another from the corona. And another model is the so-called coronal scenario. So the X-ray is dominated by the coronal, but there's like a jet-linked volume control. That's the normalization factor is controlled by the radio loss parameter. And our model selection results always supports the coronal scenario. Means that for steep spectrum radio quasars and for most radio loud quasars in general, the corona dominates the X-ray emission. However, for a small portion of flat spectrum radio quasars, a distinct jet X-ray component is necessary. And our results supports that their small scale process in their immediate vicinity of their supermassive black hole, like it's in control of their read loudness parameter of quasars. And we think that is probably related to their magnetic flux or magnetic topology. And our results also support a unification of quasars and black hole X-ray binaries. I will stop here. Thank you.
Thank you very much, Shifu, for that presentation. Very interesting work. Do we have any questions for Shifu? If there are no questions now, I do encourage you to add questions to the Slack channel if you have some. So now we'd like to go on to our next speaker. Thank you. If our next speaker could share their slides, I appreciate that. Our next speaker is Maayane Soumagnac from the Weizmann Institute of Science and the Lawrence Berkeley National Laboratory, talking to us about methods for detection of transient X-ray sources. Can I have an audio check?
Okay, do you see my screen?
I see your screen and I can hear you now, yes.
Okay, great. Okay, so thanks for inviting me to give this talk. My name is Maayane Soumagnac, and I recently finished a joint postdoc in the Computational Research Division at the Lawrence Berkeley National Laboratory and the Weizmann Institute of Science. And today I'm going to tell you about the search for X-ray transients, specifically for short X-ray transients. And the results I will tell you about has involved many collaborators, in particular Eran Ofek, who will speak tomorrow, Peter Nugent, and Guy Neal. So we've entered a golden age in the study of astrophysical transients. In recent years, advances in the field of large-scale, high-cadence, wide-field time domain surveys have provided a tremendous amount of rich and diverse new data, and have shed a new light on the transient sky. And surveys like PTF, IPTF, and ZTF, of which I'm showing the fields of view here, have provided unprecedentedly rich data sets and have led to the discovery of new types of transients. Within 2.5 years of operation, ZTF, perhaps the most impactful of this survey, has led to the discovery of more than 5,000 supernovae and a myriad of other transient events like TDEs and a new class of AGNs. And the next decade is expected to be just as important for the field of transient astronomy. Understanding the origin and nature of transient is among the key science cases for the Rubin Observatory, LSST, and the LS4 survey, and it's also the motivation for the deployment of future space missions surveying the sky across the electromagnetic field, like the Ultrasat UV satellite mission. And this new generation of cutting-edge mission poses new challenges related to the large amount of data they produce. For example, during its first 2 weeks of operation, the Rubin Observatory is expected to discover more supernovae than humankind has ever observed. So transient astronomy is said to have entered a big data area. And as more and more data is coming down the pipe, our traditional tools are starting to buckle under the size and velocity of the data, and we're being forced to rethink our methodologies and adapt tools from the growing field of data science for processing and investigating this data. So the X-ray transient astronomy, as you know, is following a similar evolution with a growing amount of data accumulating, almost 1 million detections from more than 20 years of operations of both Chandra and the XMM telescope and the Erosita all-sky survey down the corner. And this has changed the way that we work and discover transients. While previous generation of transient astronomers would have to put a lot of effort in collecting the data about a given transient they discovered, today part of the game in transient astrophysics is to mine all the archival data that is already there and develop tools to look for the needles in the haystacks and find the interesting objects that are hiding in the existing data. So in the past decades, many searches for X-ray transients have been performed using the archival data of large X-ray telescopes. And when preparing this talk, I've compiled a list of most of these efforts, which I will get back to in a minute. And in the next slides, I will try to give some answers to the following questions. What have we learned about X-ray transient from these archival searches? What were people looking for and what did they actually find? How are these searches performed? How do we find X-ray transient and what are the challenges in searching them? And how can we improve the blind searching algorithms? And I will share preliminary results from a search that we're currently performing using 20 years of Chandra archival data. So the X-ray sky is extremely variable, as you know, and transient phenomena that emit in the X-ray are extremely diverse and they vary over a broad range of timescales. So in this plot from Marloni et al., we can see how diverse the landscape of all these variable phenomena is. X-ray variable sources with timescales spanning a few seconds to a few years include galactic phenomena like X-ray binaries and other stellar phenomena, as well as extragalactic phenomena like active galactic nuclei, GRBs, TDEs, and more. And interestingly, about half of all the sources found by these archival surveys were stellar flares. But although a lot remains to be understood about these phenomena, this was not what the authors were looking for. So what were they looking for? In the early days, the studies were mostly motivated by the possibility of finding GRB afterglows, which were eventually found in the late 90s. And many of the most recent archival searches were looking for what could be a new class of X-ray transients with duration of a few tens of kiloseconds. There have been several papers in the last decades reporting the discovery of such objects and claiming they could be part of a new class of objects. And possible explanations include the disruption of a white dwarf by an intermediate mass black hole, off-axis GRBs, and in this Nature paper from 2019, it's been proposed that the latest instance of this object could be the signature of a magnetar resulting from binary neutron star merger. So this later work shown here in red, which to my knowledge are all the archival blind searches making use of Chandra data, were motivated by the possibility to find additional instances of these few kiloseconds events. And they are shown here as red dots, two of these events. And many of the blind archival searches from the past few years are looking for objects with typical durations longer than an hour, but there is a lot to be discovered still and understood about transients with shorter durations. In particular, finding and understanding supernova shock breakout event remains one of the holy grail in supernova science. And this was the motivations for a very recent work by Alp and Larsson, where the authors mined the XMM archival data in search for shock breakouts event, and they actually found 12 candidates. And it's also one of the main motivations for the blind search that I'm currently performing on 20 years of Chandra data. So I'm going to say a few words now about these events. So let's remind ourselves what we mean by shock breakouts. And what happens in a core collapse supernova. We have an explosion, and at the center, we have a very hot region with a cold region around it, and the shock is propagating outside. And at first, the shock is expanding and is actually decelerating in the beginning until it gets to a point where the density of the star is starting to decrease rapidly, and then it accelerates. until it gets to a point where it's breaking out. At this point, photons start to leak out to the observer, and this is what we call the shock breakout. And then things continue to expand and continue to diffuse. And here is an artist view of this shock breakout stage. So we think that this stage lasts from a few seconds to an hour, and it's theorized to produce a strong blast in the UV and the X-ray. And in fact, the ultrasat UV satellite, which I mentioned before, is expected to detect about 15 of these shock breakouts events per year. And as far as the X-ray is concerned, only one shock breakout has been directly observed to date. It was more than 10 years ago, and it's described in this paper by Soderberg et al. It was a very lucky detection during a scheduled observation of another target by the Swift X-ray telescope. So during this observation, while the authors were busy observing this other target, they suddenly saw this luminous X-ray outburst in their field. And later they realized that it was marking the birth of a type 1b supernovae. And this is the light curve for this event. So this happened once more than 10 years ago, but if this is indeed the signature of most core collapse supernovae explosion, there should be many more of these events hiding within the archival data of X-ray telescopes, including Chandra. So searching for X-ray transient in archival data comes with many challenges, especially if they are short. And I'm now going to talk about some of these challenges and how we can overcome them. So the first major challenge in searching for a transient, especially short and faint ones in large X-ray surveys, is that transient, especially the short ones, get buried in the background noise. And it's easy to understand if we do the math and consider, for example, a transient releasing 5 photons within a 10 pixel aperture, observed over a time interval of 5,000 seconds. So with a background value of 10 to the minus 6 counts per pixels and per seconds, we get a signal to noise of 22 for the detection of this transient. And now if we ask what would be the signal to noise ratio of the detection for the same transient, but if it was to be observed over a time interval 10 times longer, the signal to noise ratio would actually be much lower. Now short transients like shock breakouts are shorter than an hour, but if you look at this histogram of the exposure times in the Chandra archive, you see that most exposures are much longer than this time scale. And the longer the exposure is, the higher the contribution from the background noises. And so these short events can easily get hidden or buried in the background noise. And one of the solutions to this problem is to cut all the images in time into shorter sub-images of a few thousands of seconds, and then run a searching algorithm on these temporal slices. And there are, of course, other complications here because some transients may sit astride 2 images. So a more sophisticated version of this solution is to slice the data into overlapping intervals of time. But the general idea here is the same. You want to slice the data in time. And indeed, all the works shown here with red dots use this method. So you see that most of the blind searches performed in the last decades involved some degrees of slicing of the data into shorter exposures in time. Another challenge is related to source detections. How do we detect transient source in an image? So a very common method used for source detection, which I'm sure you're all familiar with, is match filtering, where you basically know more or less the shape of the signal you're looking for in the data, which is also called the kernel. And you cross-correlate this kernel or this template with your image. And here I show an example where the image is a city map. And the kernel you're looking for is this small square. And so in a place where the image and the kernel are similar, the cross-correlation will peak, indicating an actual detection. So this technique stands at the base of many detection algorithms, such as the LIGO gravitational wave detection code and many more applications in virtually any field of science and engineering, and in X-ray imaging too. It's been used extensively, for example, in the wave detect algorithm. I'm sure many of you are familiar with and using. And there are two big issues when using the traditional match filter for source detection in X-ray images. And this brings me to the last part of this talk, ideas to improve the searching algorithm. So what are these two issues with match filtering? The first issue is that match filtering can be shown to be optimal in the presence of Gaussian noise. And in the case of X-ray images, where we have very few photons and the signal from both the source and the background is Poissonian, traditional match filtering is suboptimal. And the second issue is the choice of the kernel shape, which happens to be suboptimal in many detection algorithms used in X-ray astronomy. And the solution to both these issues came from a paper from 2018 by Eran Ofek and Barak Zakai from the Weizmann Institute. So Eran Ofek will actually present their work at 10 past noon tomorrow, and I will let Eran tell you all about the Poisson noise match filter they derived and its implication for X-ray astronomy. But here is a teaser, a spoiler. The paper addresses the two issues that I just mentioned, and they derived a filter that is slightly different from the traditional matched filter, and it's mathematically proved to be optimal in the Poisson noise regime. And they also showed that this small modification they did can improve the sensitivity of the detection by a factor of 2. And in the last minutes I will share preliminary results from running a code we call T-Rex on 20 years of Chandra archival data. So what does T-Rex do? It cuts the data into shorter exposures, like I explained before, to avoid losing precious transient in the noise. It implements the mathematical proof by Ofek and Zakai as a source detection strategy, the Poisson match filter. And it includes treatment of several gory real data issues, which I will spare you the details of. For example, the fact that the Chandra PSF is highly variable over the field of view, as you know. And the results of all this is a searching tool that is sensitive to short and faint transients. There is one more big challenge we had to deal with to compute this blind search, which is very significant of this new area we are entered, where astronomers have to mine tremendous amount of data. And here is the problem. We're cutting each CCD into 64 subsquares and compute each search on one such subsquare. And this has to do with the fact that we need to deal with the PSF variation over the CCD. And if one search in one such square takes about a second, and given that there are about 15,000 images in the Chandra archive, we would need almost 2 years to run our blind search on the entire archive. And this, of course, needs a solution because we want to tweak parameters like the duration of the transients we're looking for and run it several times, etc. So to overcome this challenge, we have been running our code on the NERSC supercomputer hosted at the Lawrence Berkeley National Lab. It's a great resource that allows to do massive parallelization of codes. So if we run T-Rex on 1,000 nodes using 32 cores each, which is quite standard on NERSC, our 2 years task takes only a few hours. And this is an example of some preliminary results. So here I'm showing an image at a relatively early stage of processing in the detector coordinates. And I now move on to sky coordinates. So this is an image of the X-ray sky. And if I ask you if you see sources in this image, it's quite hard to tell. I could think of 3 areas with a slightly higher density of photons. But when we filter the image with the Ofek and Zakai optimal Poisson match filter, we see 3 distinctive blobs. And 2 of these, shown as yellow stars, are known Chandra sources. But here we have a detection that is not in the Chandra source catalog and could very well be a newly discovered transient source. And in fact, we find many new transient like this one, which are not included in the Chandra source catalog. So here I show the number of sources detected by T-REX as a function of the date of the image public release. So the orange objects have one or more counterpart in the Chandra source catalog, and the blue objects are new objects, which we found, which don't have any counterpart in the Chandra source catalog. So the Chandra source catalog only includes images that were publicly released before 2015. So this explains all these objects, all these new objects that we find after January 2015. But you see that even before this date, we find about 35% more objects, which we think is due to the improved sensitivity of our methods. And here, sorry. And here is another interesting result. This is LP 94420. It was the first flaring brown dwarf ever observed, and it was discovered with Chandra in 1999. And at this time, the scientists knew what they wanted to observe. They knew they wanted to observe this object, so they targeted this object. But interestingly, this flare was rediscovered with our method, which is a purely blind search. And here I'm showing the light curves we computed. So this event does not have a counterpart in the Chandra source catalog, probably because it was too short and got lost in the background noise. But our method allows to overcome this issue. And in fact, we think our new catalog will be completely dominated by flaring stars because they are produced by a very broad variety of nearby and rapidly rotating stars. But they will be interesting. It will allow us to characterize this population taking full advantage of Gaia, which was impossible until recently. And one thing we want to do, which I think has not been done before, is to calculate the rate of flares from coronally active stars, and in particular, the fraction of nearby brown dwarfs, such as these objects that are flaring at any given moment. So what else we think we will find? What else do we think we will find? So transient with counterparts that are small and faint galaxies will be good candidates for the shock breakouts events that I mentioned before. I estimated that we will find 5 to 10 of these in the Chandra data. And transient with no counterpart will be the signature of interesting and exotic objects, maybe neutron stars, accreting material from the interstellar medium. And this is a blind search, so we actually hope to find things that we don't know we're looking for. Spectroscopic follow-up of a large sample of this transient is crucial, and we hope to achieve this with DESI. And as I said before, in general, a lot remains to be discovered and understood about X-ray transient with the shortest time scale. And so a longer-term goal of this is to characterize all these short transients. I will also add that we're of course planning to release the catalog that we're currently computing to the community. So there will be a lot to do for people who just want to use our source catalog. And I will end with 2 points in conclusion. I rushed a bit. So largest and largest amount of extra archival data offer new opportunities to perform blind searches and make new exciting discoveries, like the ones that were made in the last decades, especially in synergy with recent advances in the field of supercomputing and data mining. And there is now a solution for matched filtering in the low number count Poisson noise regime, which was proven to be optimal and is relatively easy to implement, and which is already showing promising results with the T-REX algorithm, and more on this tomorrow at 12:10. Thank you.
Thank you, Maayane, for that excellent talk. We already have a couple of questions, so I'm going to jump straight to the questions from the audience. If you have a question, please be sure to put it in the Slack channel or here in the Q&A box. The first question is a detailed question from Errol V asking, how are you dealing with the variability of the PSF of Chandra? And before you ask that, can I ask, are you talking about like the off-axis PSF changes, or what PSF changes?
You're asking, sorry, I thought you were asking the person who asked the question.
Oh, no, sorry, I'm asking you to clarify that.
Okay, so how are we dealing with this? We're doing several things. We're basically running the search on subsquares of the CCD. We basically cut the CCD into 64 squares, hoping that the PSF will change less in these subsquares, but this is not enough because, as Eran will explain tomorrow, the match filtering, the Poisson noise match filtering that we're using, it has a PSF term in it, so it's depending over the PSF. The PSF is actually a parameter of the filter, so we really need to do a better job. And what we do is we actually let the PSF vary over logged increments that we take to be between the minimum and maximum PSF on these subsquares, and we choose the values that gives us the optimal signal to noise ratio for a given detection. So it's not as good as doing a proper modeling of the PSF, like the Marx codes allow you to do, but this, I think, we will leave for the next round of our implementation. Right now, what we're doing is trying to find the optimal values. And I will also add that we compare, of course, the value of the PSF, which is estimated with this method, with the nominal value of the PSF at this point, and we flag all the sources for which there is too much of discrepancy between these two values. So the sources come with the flag that indicate if they are suspicious to this specific question.
Another question we have here from Rafael Martinez Galarza. Thanks for the nice talk. Is your method also sensitive to things that are dipping instead of flaring, like an exoplanet transit, eclipsing X-ray binaries, etc.?
That's a good question. I would have to think about it. But we're producing light curves, so I would have to think about it and give you a good answer tomorrow. Excellent.
And then a couple more questions. Thanks for the remarkable talk. That's coming from Ugo Tranin, and they add, do you have an estimation of the false positive rate among sources newly detected by T-Rex?
Okay, so I can show a plot about this. So actually, most of the work now that we've run T-Rex on the entire data. Most of the work now is to understand this, like what are the real detections in what we have, and is there a lot of junk? Like the big part of the work now is to clean our catalog. And this is a plot where I'm showing these objects that don't have any counterpart in the Chandra source catalog. So the good thing is that most of them are close to our detection thresholds, which indicates maybe that we detect them and they were missed before because of the improved sensitivity of our method. However, there are also objects with signal to noise ratios which are pretty high, which were missed. And this is more worrying. So the good thing again is that there are very few of these objects, but because we're dealing with so much data, we cannot just go and inspect everything visually. And right now, what we think is that these objects are clusters which were removed from the Chandra source catalog just because this is the way that they chose not to include the clusters in the catalog. And because we didn't do this kind of sorting in advance, we're basically finding them. So these are objects for which the PSF that T-Rex wants to apply is much larger than the nominal PSF. And this may be an indication that these are like extended sources that were not included in the Chandra source catalog. And this is why we think they don't have a counterpart and are new sources. So this could be one source of like false positive. And yeah, I would say that now like most of our work is to try to quantify this.
Thank you. We have lots more questions. I'm just going to ask one more, and the others in the Zoom channel, please add your question to the Slack. If Maayane has time later to answer it, hopefully she can. This question is from Lorena Hernandez Garcia, and they're asking, have you found counterparts of your sources at other wavelengths that confirm the transient nature?
So we've found the flaring star that I showed is an example of something that we know is, well, not a transient, but like a variable source that was missed in the Chandra source catalog and that we are finding. So we basically, that's not in a different wavelengths, but what I mean is that we have checked that some of the things that we find are physical. So that's a good big start. And we haven't done yet the cross-matching with Gaia. We could cross-match this catalog with many catalogs of virtually any catalog of source to check what we have there, but this is what we're doing now. And I don't have results yet, solid results yet to show you, but we are definitely finding physical things and existing transients and existing variable things.
Awesome. Thanks again for an excellent talk. A lot of discussion in the Slack and here. Please put your questions there for Maayane if she has time to address them later. Will the next speaker start to share their slides, please? Our next speaker is Francesco Ubertosi from the University of Bologna and the Istituto Nazionale di Astrofisica. Is going to talk to us about the deepest Chandra view of RBS 797.
Okay, so good afternoon. I am Francesco Ubertosi, a first-year PhD student at the University of Bologna. And today I'm going to talk about a recent Chandra large program observation of the galaxy cluster RBS 797. So a very brief introduction. The impact of AGN activity in galaxy clusters is best traced by X-ray cavities excavated by radio lobes. And in particular, many nice examples of multiple pairs of X-ray cavities have been found by Chandra, either aligned along a common axis or misaligned, possibly following jet reorientation. And an interesting example of radio X-ray interplay is the galaxy cluster RBS 797. Past Chandra observations of this cluster revealed two deep X-ray cavities in the east-west direction, and radio observations with the VLA unveiled radio lobes filling the cavities. Additionally, in the radio images, there are hints of radio extensions also in the north-south direction. At higher resolutions, two pair of perpendicular jets have been discovered and a VLBI observation of the radio core revealed two compact point-like sources. So GT et al. 2013 combined these findings and proposed that either a reorientation event of the AGN jets could explain the misaligned outburst, or that the two point-like components consist of two active supermassive binary black holes that have excavated the east-west cavities and are also responsible for the north-south extensions. So in order to shed lights on this peculiar system, Chandra large program observation of RBS 797 has recently been performed, and from the images and also by combining different imaging techniques, we found evidences for the presence of two additional X-ray cavities north-south of the nucleus, and these are well matched by the radio extensions also in this direction. And thus, while many galaxy clusters have been observed to have multiple pairs of X-ray cavities, the peculiarity of RBS 797 is that the four discovered X-ray cavities are all at the same projected distance from the center. So in order to Yes, thank you. In order to investigate the history of the two pair of cavities, we compared different estimates of cavity ages from X-ray data, and we found that both cavity systems are between 10 to 50 megayears old. And it is important, however, to note that these X-ray cavity ages suffer from systematic uncertainties related to the assumptions of the different methods, and also from projection effects that affect the true shape and distances of the cavities from the center. Additionally, with the available radio data, we could only set upper limits on the radiative age of the emitting plasma within the lobes that are still quite consistent with the X-ray estimates. So altogether, the cavities are nearly contemporary because the outburst interval between the east-west cavities and the north-south cavities is less than 10 megayear. On the one hand, reorientation might happen on shorter timescales, so we cannot definitely exclude that a reorientation of the agent jets might explain the perpendicular outburst, but the typical outburst interval of known galaxy cluster with multiple pairs of X-ray cavities is higher than our 10 megayears estimate, so the possibility of having a dual active supermassive black hole system in the core is still tantalizing. So I'm leaving my conclusions here, and thank you for your attention.
Thank you very much, Francesco. The two questions there are for the previous speaker. I'm going to put a message in the chat for anyone that has a question to ask a question there. I think we should move on to the next speaker now.
Okay.
So in the Slack channel, you can leave a question for Francesco.
Thank you.
Our next speaker can share their slides now. Our next speaker is Rhea from the University of Montreal, who's going to talk to us about bringing machine learning to X-ray spectral analysis.
Great, thank you for the introduction. Like you mentioned, my name is Rhea. I'm a first-year PhD student at Université de Montréal under the supervision of Professor Julie Slavacek-Laurando. And today, I'm going to be talking to you about two different machine learning kind of algorithms and analysis that we've been trying to bring to the analysis of X-ray spectra. We're going to hear a lot of other wonderful talks throughout this conference on using machine learning for X-ray imaging. So this is a little bit different, and I'm extremely glad for the talks that have already happened, discussing model comparison using a Bayesian approach. The first half of this talk is actually going to discuss doing a machine learning approach to model comparison in the context of galaxy clusters, and the discussion of the response matrix, which will be the second half of this talk. For a brief outline, I'm going to go over galaxy clusters, just to discuss their anatomy, what their structure looks like in their thermal emission. This is a specific test case we're using to test our machine learning algorithms on X-ray spectra. Then discuss the main problem that we focused on in our first paper using machine learning to analyze X-ray spectra. and an application of this to a real galaxy cluster. And then finally, the future work focusing on how machine learning can be used to deconvolve response matrices from X-ray spectra, and why in the world would we want to do that instead of using the normal forward fold approach. So galaxy clusters, let's jump right in. So galaxy clusters are at their core simply a collection of hundreds to thousands of galaxies with a typical mass of 10 to the 14, 10 to the 15 solar masses. These are very rich systems, multiple different wavelength counterparts. You can see it very clearly here in this image. We'll note that the mass distribution, interestingly enough, is primarily under the form of dark matter. The majority of the baryonic matter, however, is in the intracluster medium, which is a hot diffuse plasma. We'll discuss that in a second, which pops up in the X-rays. Here you can see the Chandra observation in blue. And then only 3% of the total mass distribution is actually in the galaxies through visible light. I'm not going to talk at all about radio. If you're interested in that, please bother Merilou. She's here as well. So I'll move on. So what does the intracluster medium look like? This is this hot ionized plasma with a typical temperature of 10 to the 7 or to 10 to the 8 Kelvin. You can see this beautiful Chandra image of the Perseus cluster. These are just counts in purple. You can see that there's a whole lot of structure. We see some cavities, or also known as bubbles, which we believe are inflated from jetting activity from central AGN, evidence of AGN feedback. And there's also a lot of other fascinating physics happening, cold fronts, merger-induced sloshing. I'm not going to talk about that. I know there will be some discussion on that later. I just want to convince you that galaxy clusters are fantastic, and we can certainly study them in the X-rays. So since I wanted to talk about spectra, I thought it would be only fair to show you what a nice galaxy cluster spectrum might look like. So what this ICM or intracluster medium looks like. The continuum portion of the spectrum is due to thermal bremsstrahlung emission. And superimposed over that, we have our standard line transitions, with the strongest being this iron K alpha line. So how are we going to use machine learning to study galaxy clusters? Well, our initial problem is quite simple. How many temperature components do we need to describe the ICM? We know that we can't simply say, okay, the ICM has this temperature, but rather it's a continuous distribution of temperatures. But how many discrete temperature components do we need to describe this continuous distribution? And for a follow-up question, how would you determine the optimal number? If you're Hannes Buchner, you're probably thinking, let's do a Bayesian approach, and I couldn't agree with you more. However, what if you wanted to do another approach to help validate your results, or what if you have a whole lot of spectrum and you need to quickly do the fits? And of course, finally, you need to ask yourself why this matters. Do we really need to know the optimal number of thermal components, or can we get away with estimating 1 or 2 thermal components? First off, we're very interested in the actual true temperature distribution. So this paper, Sanders et al. 2004, shown here, goes through the Perseus cluster, and by fitting temperature or thermal components of fixed temperatures, they're able to show that the majority of the emission in the Perseus cluster in the X-rays is described by 2 to 3 temperature components. They also demonstrated the importance of the number of temperature components on extracting the true metallicity from this ICM, which is extremely important for testing different cosmologies. So our proposed solution is to use a machine learning algorithm, a mix of algorithms, to systematically determine the number of underlying thermal components. So the first thing we did is we constructed a synthetic spectrum, or a large set of synthetic spectra for single, double, triple, and quadruple temperature component models. We then used PCA analysis to create the covariance or projection matrices based off of our training set. Then we used a random forest algorithm on these principal components for a synthetic training set to classify the spectrum by their number of underlying thermal components. So the basic idea is you give me a spectrum, I tell you if it has 1, 2, 3, or 4 underlying components. And thank you very much, Becky Nevis, for discussing random forest, so I can skip that. And then finally, for the test set, we project our test set spectra onto our principal component basis, and then we verify the viability of this trained algorithm on the projected test set. So what does our synthetic data look like? We randomly selected temperatures and metallicities from a uniform distribution You can see the distribution for temperature and metallicity. We created 40,000 spectra in total. 90% were for our training set, 10% were for our test set. Everybody loves to see code in a presentation, so I added this small image here. The only interesting thing you need to note here is that we do have to assume some sort of RMF, or response matrix, and ARF. And this is what a typical spectrum might look like. So why are we doing a principal component analysis of the ICM spectra to begin with? Why aren't we just pushing the spectrum directly into the random forest algorithm? Well, the first really important thing is that it's actually reducing our input dimensions. So instead of having to worry about the 600 channels that we have in our spectrum, we can actually reduce that to only 25 input dimensions. The idea is that principal component analysis is pulling out the important features in the spectrum while ignoring the less important features. And we're hoping to find better defined categories. Because if you think about an X-ray spectrum and you look at it, it might be very hard to tell by eye if it has 1 or 2 or 3 or 4 underlying thermal components. So we're hoping that becomes a little more evident in the principal component space. And what we see here is, to a certain extent, yes, to a certain extent, no. I've color-coded the these different dots based on the number of underlying components, and these are projections in the principal component space. You can see things start to fold and really start to get into some better categories. It's not great, but it's certainly helpful. I'm not going to discuss this, but if you're interested in the paper, we have a discussion of what these different principal components actually mean physically for our spectrum. When we apply the random forest application, or when we apply the random forest on the PCA pre-processed spectra, you can see here in our response matrix that we do a pretty good, or not a response matrix, sorry, in our confusion matrix that we do a pretty good job of pulling out the true number of spectra. For those of you who are not familiar with confusion matrices, the way you read this is the number of true underlying thermal components. In this case will be 1, and 83% of the time we're also predicting 1. In this case, 12% of the time we're predicting 3 when there are actually only 1. The name of the game here is to get a diagonal confusion matrix. As you can see, this is mainly diagonal. And when we compare our PCA preprocessed to non-PCA preprocessed, we note that it's a stronger diagonal confusion matrix, meaning it's better to do the PCA preprocessing than not doing the PCA preprocessing. There's much more in-depth discussion about that in the paper. Of course, no machine learning test or introduction to machine learning test is complete without applying it to real data. So we decided to apply it to one of the most famous galaxy clusters, the Perseus cluster. And just to give you a brief idea of why we decided to go with the Perseus cluster, it's the brightest galaxy cluster in X-rays. There are over 2 megaseconds of exposure, or Chandra, and it appears in over 70 publications on the archive. It's an extremely complex galaxy cluster. There are bubbles in the ICM, there's cold front, there is evidence of Kelvin-Helmholtz instabilities, and of course, turbulence. So this is a really fascinating target for which we want to get the temperature distribution down really well so we can start to understand these features. So what we did, and the basic idea of this, is we took 2 observation IDs of those 2 milliseconds for about 200 kiloseconds worth from the archive. This is just the raw image. I've highlighted the 2 main cavities in the central BCG in Perseus cluster. We applied a weighted Voronoi tessellation binning algorithm to break up the regions into similar signal to noise regions. And then we extract the spectra in those regions and pass that through our algorithm. So applying principal component analysis and applying the random forest algorithm that we've already trained. And what we find is that the majority of the Perseus cluster here in blue is denoted by 2 underlying thermal components, which is the same thing that the Sanders 2004 paper and other papers about the Perseus cluster have found. So this was a wonderful verification. Also in the open source code called Pumpkin, there's a link to it later, and it does all of this for you. It also then tells you what those temperatures are likely to be using Sherpa. There's a much larger discussion of that in the paper as well. Okay. Great, I have 4 minutes, perfect. So I wanted to talk about some of the future work. So one of the main things you all probably noticed and might have scared you, which would have been very reasonable, was our treatment of the response matrix. The response matrix is, as you know, a very tricky beast that we normally deal with by forward folding it when we're doing our fits. So our question is, how can we deconvolve our X-ray spectra? How can we really pull out the true spectrum from our observed spectrum, knowing our response matrix? And the reason why I want to do this is because we want to be able to apply other machine learning algorithms more generally to the X-ray spectrum, and there's no simple way to fold the response matrix into the training, unless you train over all response matrices, which can be extremely expensive and quite honestly, a little unfeasible. So why is deconvolution important in the first place? Why do we even care about this response matrix? Well, we know our spectral response function has a really strong effect on the observed spectrum. And for machine learning applications, as I mentioned, we want that clean or true spectrum. Here I've taken the response matrices from two regions, random regions, from a random observation from the Chandra archive, and using the same underlying thermal component, plotted what the X-ray spectrum would look like. By eye, these two don't look too different, but if you look at the relative difference between these two spectrum, you notice that the response matrix really is having a strong impact on what we observe. So if this is an indication that the response matrix really is important. And so what have we tried? Well, we tried a standard inverse problem analysis using techniques from actually just normal ways to do deconvolution, solving the inverse problem. The issue is that the response matrix is extremely singular, or the problem is ill-posed. What that means is that it's very hard to do an inverse, and you introduce a lot of spurious noise that will mess up your inverse problem and make it impossible to find your true spectrum. We have a research note on that called Data-Driven Approach to X-ray Spectral Fitting, Quasi-Deconvolution in the archive. And the main reason we wanted to do this deconvolution in the first place was to use these spectrum for a machine learning approach. So we thought, well, if we want them for a machine learning approach, why don't we try a machine learning approach to deconvolve the spectrum? And that's exactly what we've been doing. We've been using a technique or an algorithm known as the recurrent inference machine. It is a combination of recurrent neural networks and classic Newtonian stepping. I'm not going to talk about it at all, except to say that we're currently working on this, and it shows great promise for doing deconvolution of X-ray spectrum. And I will end on the note that the reason why we're doing this type of deconvolution is so that we can then use these deconvolved spectrum to train algorithms to pull out important features from the spectrum, such as the temperature metallicity, which then can be used either to inform our fits using Sherpa for our first guesses, our best estimates, or to build a prior parameter distribution and a prior parameter space for those, if you want to go the Bayesian approach. Using an idealized spectrum, so idealized deconvolved spectrum, this KDE plot, kernel density estimation plot, shows us that using a standard CNN that we pulled from another paper does a very good job at pulling out the temperature, the true underlying temperature of spectrum, which tells us that we really need to get down this problem of deconvolution so that we can then apply it to this field. I just listed some other papers, some other work that we've been doing using this exact same idea, which is why I've called it transfer learning, but in optical integral field unit spectroscopy. I'm sorry, I know that was quite a lot, especially for 17 minutes. But with that, I'm going to come to a conclusion. And if you have any questions, please feel free to ask. Here are the links to the paper on archive and the GitHub link to the software.
Thank you, Carter. I'm waiting for your slide to render. Thank you.
Oh, sorry about that.
Do we have any questions for Carter from the audience? Please add them to the Slack or put them in the Q&A here. We have a question from Michelle on the Slack channel, who's asking or stating that they're interested if you've considered a machine learning version of PCA, and they give an example autoencoder as a first step.
No, we have not. Though I would love to talk to you offline about that, get your thoughts on it, so that we could implement it. So thank you very much for that.
Mm-hmm. Any additional questions? Sorry, I don't see any additional questions here.
Okay.
I have a real quick question for you though about the RMF. The fact that you have to consider an RMF, if you were doing comparisons like say of different epochs of some observation, does it limit your ability because you have to use an RMF?
Extremely, and that is actually one of the main reasons why we only use 2 observations of the Perseus cluster for this application, because if we realize that if we were to extend it to more that were more spread out in time, the RMF becomes really important and completely throws off the analysis, which led us to this conclusion that we have to handle the deconvolution somehow.
Yeah. So that would be the only solution you could see. You don't expect to have a time-dependent calibration model somehow.
There's absolutely, that is an avenue to go down. That's not the avenue that we chose to go down.
Right. Excellent. Any more questions or comments? Okay. Thank you, Carter, again for that excellent talk. And I am now going to ask our next speaker, Dennis Leahy, to share their slides and unmute themselves if possible. There you are. Excellent. Our next speaker is Dennis Lee. He's coming to us from the University of Calgary. He's going to talk to us about new features in the 35-day cycle of Hercules X1.
All right. Okay. Well, this is basically an update on some work that's been done recently by myself, University of Calgary, and some of my students based on recent observations of Hercules X1. So I start with just a brief reminder of what the system is. It's a neutron star undergoing Roche-Lobe accretion with an intermediate mass companion, 2.3 solar mass star. It's very well studied over many decades. We know its orbital period and spin period, and also the fact that it has a very distinctive 35-day cycle, which is about 20 orbits in X-rays, which is caused by the accretion disk obscuring the X-rays from the central source as the accretion disk rotates over a 35-day period. There's also an optical cycle, which is roughly at the orbital period, which is the excess optical light created by X-ray heating of the front face of the companion star, and the cycle is due to the changing viewpoint of the observer as the system rotates. Okay, so the kind of data I'm going to talk about, some is from the AstroSat satellite in the past 3 years of observations, and I'll also mention something about MAXI and SwiftBat monitoring. So one thing that was found just last year, looking at LAXPC observations, which is a large area proportional encounter, is by looking at the softness ratio hardness, or the softness ratio intensity diagram. I'd like to use softness ratio rather than hardness ratio during a main high state. So this is the main high state. Is shown as orbital phase, and there's some dips and eclipses over here. So this is pre-eclipse dips in here. You clearly see 2 different behaviors in hardness ratio. This hasn't been noted before. When we do the plot here, we see that the slow dips show absorption, but the rapid dips don't show any absorption. Okay, so there's more follow-up to be done on that. We also have UV observations, basically 150 nanometers. And we see a strong orbital modulation, somewhat similar to the optical modulation. But in UV, we're sensitive to the X-ray heating of the face of the companion. So this is just as a model here with the shadow of the accretion disk on the companion at different orbital phases. We compute the X-ray heating and we get modulation shown by this green or dashed blue line. But also in the far UV, the accretion disk is a significant emitter, and you have a calculation of the emission from the X-ray, the heated accretion disk as a function of orbital phase. So it's just changing slowly because the disk takes 35 days to rotate. So this is only about a 10-degree rotation of the accretion disk. And the sum of the two fits very well the data. So ongoing data is, we've got several other observations during other 35-day phases, which show modulation, which is quite different, but a strong modulation. So we're working on using that. It's a very strong constraint on the shape of the accretion disk because it's very sensitive to the shadow. So last thing I'm going to mention is the monitoring observations, mainly with Swift-BAT and also the MAXI instrument on the space station, but also there's older RxCSM observations. But what's nice is both of these are sensitive enough to clearly see the 35-day cycle and all of these persistent dips which occur every cycle. So we've used a couple of different analyses, cross-correlation analysis to actually measure the cycle lengths. So we've got a long-term record of the cycle lengths. And I'll end with this slide. The other thing we've done is create the mean MAXI light curve and the mean BAT light curves. And with these, we can get mean, so here's the mean light curve during the main high and during the short high, just for MAXI, but we get the softness ratio shown in red here during the main high and short high on average, which is new, and we could use that to get the average column density throughout each orbital cycle. So during the main high, we get the decrease in column density. This is from the accretion disk and at the beginning of the main high, and then the increase in column density at the main high, and actually a very similar pattern during short high, all over a shorter range of orbital of 35-day phase. Okay, I'll stop there. There's ongoing analysis with all of this. I'll end my presentation.
Thank you very much, Dennis. That was very interesting. I'm especially find remarkable the models that you were showing us and how well you can constrain the shapes of the disk. Is there any degeneracy amongst those
Yeah, there
solutions?
certainly is. The main problem or the main degeneracy is the system inclination. If we specify the system inclination, the disk geometry is determined very well. I'm still working on trying to get better system inclination. I was hoping that modeling the UV data with these nice shadows would break that degeneracy, and it helps a bit, but it doesn't really nail the system inclination.
Excellent. Thank you for that presentation, and thank you to all the speakers from this session for their presentations. I remind you all that you can always find the entire schedule for our workshop at our website, which I'm sharing with you here. And I also would like to point out that tomorrow we have an extra day, full day packed, starting again at noon Eastern and going on and on until 3:30 again. So thank you again for joining us, and I hope to see you tomorrow. Have a good evening, everybody.